Let's turn to page 4 in your packet. Okay, so today we're talking about related rates. Related rates is really the bulk of this unit. Again, this unit, we're not going to do a test. It'll just be a quiz. It'll just be really 3 topics: related rates, L'Hopital's rule, and linear approximation. We did linear approximation yesterday. We are kind of already knew how to do that. It was just tangent line equation and then plug in the decimal, right? So related rates kind of has a word problem feel to it, because everything is going to be with respect to time. So you're going to see these problems where time is the underlying variable, and we're going to see that impacting the entire problem. This is also an application of implicit differentiation. So with implicit, remember how we found the derivative for y, and y squared will become like 2y, and then we would attach dy over dx. In this unit, or for this related rates, every variable is going to be a dependent variable. It's not just going to be y. So now it could be the rate of change of the radius with respect to time, the rate of change of the length of the square with respect to time. So now every variable is going to get a d over d, a derivative treatment. So it could be, for radius, could be dr dt. For x, it could be dx dt. And for perimeter, it could be dp dt. So now our independent variable is no longer x. Our independent variable is now going to be t. And a lot of times the variable t is not going to show up in your equation, but it'll be the underlying variable. So it'll always have its impact on every variable once we find the derivative. So we're going to find the derivative the same way that we did with implicit. It's just instead of attaching a dy over dx, now we're going to attach a different derivative variable for that r, x, or p. So here are the steps. We may not necessarily do these steps in order, but we have to gather all this information in order to solve for the variable we're solving for. We want to be able to write out what we're given. We want to be able to write out what we're trying to find. We always want to start off with an algebraic or geometric equation that relates the variables together. So we're always going to start off with an equation that we recognize. It could be Pythagorean theorem. It could be perimeter of a square. It could be circumference of a circle. It could be volume of a cone. Right. So we always start off with some geometric equation that is going to allow us to relate the variables that are in play in the problem. And then we find the derivative of that equation with respect to time t. So this is really the only calculus step in our entire process. Once we find the derivative, then it's just a matter of plugging in and solving for whatever variable we're looking for. Here's an important note. I will stress this when as we do each problem. Remember that when the item is getting larger, the rate is going to be positive. If the item is getting smaller, then we want the rate to be negative, regardless of direction. And that's something that we have to kind of get used to, because we just got done with particle motion, where moving right is positive velocity and moving left is negative velocity. Now, positive and negative has no connection with direction. So we have to visualize the problem and ask ourselves, wait, is that value getting larger over time? If it is, we want that rate to be negative. If that value is getting smaller over time, then we want that rate to be negative. All right, so let's look at example 1 here. It says the size of a square are increasing at a rate of 5 centimeters per minute. How fast is the area increasing when the sides measure 15 centimeters in length? So you see mentions of area of a square. So that's what we're going to start off with. We're going to start off with the area of a square. What is the area of a square? What would you say the formula for area of a square is? Yeah. And what do you know about the length and width? They're the same, right? So it could be length times length, it could be width times width. I'm going to say x times x, and I'll let x represent the side length. You can use any variable. I just prefer to use x because we use x as our go-to variable here. So a equals x squared. We know the side lengths are the same for a square. Now we're going to find the derivative, get that out of the way, because then we can see all the variables that we're working with, and then we can just assign values to variables. So just like how we would find the derivative of y would become 1 dy dx. Now a's derivative, that's a to the first power, right? So a is just going to go down to a constant. So it'll be 1 times, but now it's going to be the derivative of that variable with respect to time. So it'll be what? What's the variable here? dA over dt. Yeah. So time is going to be the underlying. You see there's mentions of time all the way through this problem. Okay. Equals x squared. What's the root of x squared? 2x. Now, x is no longer the independent variable, time is, so this is also going to get impacted by time. So times what? dx, yep, dx over dt. So every variable is going to get mentioned in that derivative, and it's always over time. Okay. All right, let me talk about what these variables mean. So we can kind of imagine, so we can begin to assign some values to these variables. A represents the area of the square at a specific moment in time. X represents the length of the square at a moment in time. Appreciate it. Thank you. Thanks. No problem. X, yeah, so X represents the length of a square at a moment in time. Dx dt represents the rate at which the length of the square is changing, right? Okay. And dA dt represents the rate at which the area of the square is changing. So we'll keep that in mind as we look at some of these values here. It says the sides of a square are increasing at a rate of 5 centimeters per minute. So if you had to guess, what do you think this is describing? Which variable is this describing? Is it the a? Is it the x? Is it a dA dt? Or is it a dx dt? Sides of a square are increasing at a rate of 5 centimeters per minute. What would your guess be? Okay. Well, we see sides of a square, right? So it can't be area, right? It's either going to be x or dx dt. So which one do you think it'll be? 5 centimeters per minute. Yeah, dx dt. So there's all these words that kind of give us context clues that there's a time component to this value. You see the words increasing, you see the word rate, you see the word centimeters per minute. So that's a big hint. So our units that they give us is going to be a big help for us, because we're going to look at the unit and be able to quickly decide, okay, I see a time component, so it's got to be some time related variable. So we know that dx dt is going to be positive 5. Yeah, all these words also, like you see the word increasing and rate, they all kind of have this movement feel to it. And anytime that is a movement feel to it, it's always going to be a time related variable rather than just like a static value. Now, how do we know that this is a positive 5 and not a negative 5? There's something that gives it away. How do you know this rate is a positive and not negative? Increasing, yeah. So if something is getting larger, you want that rate to be positive. So the problem is really going to tell you to make the rate positive or negative. You have to look at the context clues and decide for yourself whether that rate will remain positive or needs to be turned to a negative value. Okay. How fast is the area increasing? What are we looking for here? Which variable do you think that's referring to? How fast is the area increasing? We know it's area related. Is it A or is it dA dt? Right. There's some key words here. The word fast, the word increasing. So what do you think? dA dt, right? There's these movement words associated with the variable. So we know that we're looking for dA over dt. Okay. When the sides measure 15 centimeters in length. So finally, what variable is going to hold that information? That's just going to be what? 15 will be which variable? Two variables left, right? It's either the x or is it the a? X, yeah. So that's a side length, right? So x is equal to 15 centimeters. So now we're just plugging all this into my derivative equation. I'm solving for dA dt. Do I have enough to find the dA dt value? Do I have x and dx dt to plug in? Yes, yeah. So we can just go ahead and solve for dA dt. So the rate of change of the area of the circle, sorry, of the square is 2 times x, which is 15, times dx dt, which is 5. Okay, multiply all this out. So, you get to use your calculator in this unit here. So we get 150. And then we also have to find our own units for this problem. So the way you find your units is you look at whatever variable is coming from. We have area and we have time. And then so we have to make sure we include those units and divide by one another. What do you think the area for this, what's the area unit for this problem? That's centimeter squared. So we have to make sure we include that centimeter squared. And then the time component is minutes. So centimeters squared per minute. So if you're ever trying to decide, wait, what's my unit here? Look at your variable. Your variable is going to tell you enough clues to help you figure out what units to use. So area is centimeters squared. Time is minutes. We see them divided by one another. So we're going to divide our units by one another as well. Right. So it makes sense that since our size of our square is increasing, we expect the area to be increasing as well. It makes sense that we're getting a positive rate. So at the end of the problem, you should never be trying to decide, okay, do I have to change the size for my rate? You should be looking at it and saying, does it make sense? Okay, and if the rate doesn't make sense, you have to go back and look, wait, maybe I didn't start with the correct sign for one of my rates, and that's why I'm ending with a sign that's not making sense at the end of the problem. All right, example 2. We have a 25-foot ladder leaning against a vertical wall. The bottom of the ladder is being pulled horizontally away from the wall at a constant rate of 3 feet per second. How fast is the top of the ladder moving, and in what direction when the bottom of the ladder is 15 feet from the wall? So we see that as this ladder is falling, it is still maintaining this triangle shape, this right triangle shape that we see. So I'm going to call this length X. I'm going to call this vertical side Y, and I'll call the hypotenuse Z. So what formula can we use that's going to connect the three sides of a right triangle? Yeah, Pythagorean theorem. So we're going to start off with that. X squared plus y squared equals z squared. And now we have our starting equation, just like how we had our starting equation for example 1. And we're just going to move into the derivative. And as we move into the derivative, a bunch of d over dt will show up for each variable. So x squared, what's x squared's derivative? Yep, 2x. And we're asking for x's derivative with respect to time. So times what? Yeah, dx over dt. Yeah. Every variable is going to get the time treatment. Plus y squared becomes 2y times dy over dt. Yeah. And then equals 2z dz over dt. All right, every variable here, there's 6 variables here. We have to we're going to list them out and see if we can account for each of them. Let me talk about what each of these mean. X and Y and Z, they represent the side length of our triangle at a moment in time. Dx dt tells us how fast is this horizontal segment of my triangle changing. Dy dt tells us how fast this side is changing, or side length is changing. And then dz dt tells us how is the hypotenuse length changing over time. So off to the side here, I'm going to list out these variables that we want to account for. Okay, we do want to save a little bit of space on the right because we are going to do a part B a little bit later. Okay, so we go back to our problem here and see, reread the problem. A 25-foot ladder is leaning against a vertical wall. So where do you think that 25 is going to be associated with? See, yeah, 25-foot ladder, that's the hypotenuse. Okay, the bottom of the ladder is being pulled horizontally away from the wall at a constant rate of 3 feet per second. What do you think this is talking about? Good, dx over dt. Well, first off, we know it's got to be some time component because you see per second, you see being pulled, you see constant rates. So all these hints of movement, we know it can't just be x, y, or z. It has to be some sort of a rate. So, and we know it's going to be involving the horizontal component. So it's dx dt, 3 feet per second. Now, it's being pulled left, but we don't care about the direction, right? We care about what's happening to this length. Is this length going to grow larger or smaller as time passes? Larger, yeah. So as the ladder gets pulled away, we can expect this base length to get longer over time. So it makes sense that we're having a positive rate. Okay, how fast is the top of the ladder moving? All right, what is that referring to? dy over dt. Yeah, we're asking about how fast that is changing. Okay, so that's the unknown, question mark. But what do you expect out of dy dt at the end? Do you expect this to be a positive or a negative value? Negative. Why? Good. Not because it's going down, right? Sometimes going down could increase something. So I purposely drew it this way, going left, because I want to make sure that, okay, just because going left doesn't mean that we get a negative. Going down, we're expecting negative, but it doesn't always have to be that way. The direction is not what matters. It's the fact that you can imagine this side length shrinking. When the bottom of the ladder is 15 feet from the wall, where's that 15 going to go? X, yeah. So the goal is that we can figure out 5 out of the 6 variables, because then we can plug it into the equation and solve for that missing variable. So there's two that's still unaccounted for. So let's look at to see if we can figure out just by what we know. I have x, y, and z. These are all side lengths of a right triangle. I have x and z, but I'm missing a y value. What do you think we can do to figure out the y, the length at this moment in time? Use what? Yeah, Pythagorean theorem, right? A squared plus b squared equals c squared. Plug all this in and solve for y. We can also see that this is a variation of a 3, 4, 5 right triangle. It's just a multiple of it. So anybody know what this y could be? 20, yeah. 3, 4, 5 multiplied by 5. I'm going to get 20 here. But we can also figure out by inserting into this and just solving it using those numbers. Now, another thing that we need to be able to figure out before we plug in is that we think we can figure this out just by thinking about what's happening. dc dt is asking how fast is this length changing over time? What do you think the rate of change for z would be? 0. Why is this 0? Yeah, that ladder doesn't change, right? That hypotenuse is going to be 25 feet at the beginning of the problem. It's going to remain 25 feet throughout the problem, right? That hypotenuse is never changing. Now, every Pythagorean theorem is going to be different, right? Or the problem is going to be different. Sometimes the problem may have all three sides changing. There's different variations of Pythagorean theorem problems. And depending on where things are moving and what's happening, this is not a guarantee every time. It's just for this problem, we can convince ourselves that the ladder, the hypotenuse is never changing. Okay, so now everything can plug into our equation here. So go ahead and try that. Replace your x with 15, replace y with 20, replace z with 25, replace dx dt with 3, replace dc dt with 0. We should be able to solve for dy dt because that's the only leftover variable in our equation. Okay, this is what I got. So that 0 is nice, cancels out that right side. We still have to multiply and subtract that value over. I get 90, negative 90 over 40, which is negative 9/4. Now, algebraically, we got a negative number, but it should make sense, right? That negative value tells us that vertical side of my triangle is decreasing at a rate of negative 9/4 feet per second, because as the ladder is sliding down, it's causing that vertical side to get shorter. Okay, part B. Part B says, at what rate is the area changing when the bottom of the ladder is 15 feet from the wall? So this is going to be at the same moment in time, so we can reuse everything that we gathered from part A. So let's see, dy dt is negative 9/4. So area, what's the area formula of a right triangle? One half what? Yeah, 1/2 base times height, right? Basically half of a rectangle, 1/2 base times height. So I'm going to use x and y since we've already established those variables. We want to find the rate of change of the area of a triangle. So we're trying to find dA dt. So we're going to find the derivative of the left side. A becomes dA dt. That's easy. But on the right side, if I want to find the derivative of 1/2 xy, what process do we have to make sure we go through? Product rule, yeah. So we have two variables being multiplied. We got to do f prime g plus f g prime. So let's see if we can set that up. Okay. Let's go down each of these terms one by one. What do you think 1/2 x will turn into? 1/2 what? The x disappears, but then what goes in place of the x? 1/2 what? Dx. Good, 1/2 dx dt, right? The 1/2 stays because it's a coefficient. The x goes away to a 1, but we need to attach dx dt. The g is the y, no changes. The f doesn't change, 1/2 x. And g prime, what does y become? dy over dt, yeah. Okay. That's the hard part, getting to the derivative. Now we're just plugging everything in. We have everything from part A to insert, right? This is at the same moment in time as part A, at the moment when the bottom ladder is 15 feet from the wall. So replace your x with 15, your y with 20, your dx dt with 3, and your dy dt with -9/4, and we can find dA dt. And in the end, what do you think your units of measure is going to be? Area and time, right? What's the area unit? Right, two-dimensional unit, so feet squared, yeah. And then the time component is seconds, yeah. So square feet per second, right? So that's how you establish your units. Look at your variable, and your variable will tell you what units to use. In the calculator, it should give you something like 105/8 or 13.125 square feet per second. Okay, next page. All right, example 3. A spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area of the balloon at the moment that the surface area is 64 pi. Now, all these volume and surface area formulas, they'll be given to you. You don't have to memorize those like cylinders, cones, all those formulas. The formulas that I do expect you to know are the basic ones, like area and area of a square, area of a rectangle, area of a triangle, area, circumference of a circle, Pythagorean theorem. Those are all the ones, right? Everything else, the more complicated formulas, they will be given to you. So we have volume of a sphere, which is 4/3 pi r cubed, and surface area of a sphere, which is 4 pi r squared. Same thing on the AP exam. AP exam, they will give these formulas to you as well. They're not going to ask you to memorize these formulas. Now, we know that with related rates, we're going to have to involve the derivatives of these. So let's just go ahead and find the derivatives and get the calculus out of the way. Because after that, then it just becomes a puzzle. We're just trying to figure out, okay, where the pieces go to eventually solve for our missing variable. Okay, so let's find the derivative of each of these and just get the calculus over and done with. Okay, so v becomes what? V's derivative is 1 times what? For every variable gets impacted by time, so v becomes, yeah, dv/dt. Fourth, there's pi. That's just a coefficient. Remember, pi is not a variable. We don't do product rule here. Fourth, there's pi is going to stay. It's not going to go anywhere. It's the r cubed that's getting impacted because that's the variable that we have to go through power rule. So r cubed becomes what? Times. Can't stop, right? Because r is also getting impacted by time. So times dr/dt, yeah. Let's do some cleanup here. The 3's can cancel out. So we have a variable that tells us the rate at which the volume is changing. We have a variable that indicates to us how the radius is changing. Okay, so so we can stop there and move on to the other equation. S equals 4 pi r squared. Every variable gets impacted by time as well. S becomes what? Yes. ds over dt. 4 pi r squared becomes what? Bring down the 2, 8 pi r, and then we still need a d r over dt. So if you look, we have 4 different equations here. You got volume equation, you got the surface area equation, you got a dv dt equation, you have the ds dt equation. It doesn't mean that we're going to use all of these, but these are what's available to us. And we have to kind of decide, okay, how can we use these equations in a way where eventually we can get to our answer. But now that we have everything in front of us, let's see if we can gather some information and assign some of these values to variables here. Okay, so let's go back to our problem here. A spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Okay. Look at the description, look at the units. Can we decide what variable will be best suited based off the description and the units? 10 cubic centimeters per second. Okay. So cubic centimeters, that's a 3-dimensional unit, right? So that has to be involving what? Volume. So it's either V or dv dt. Which one do you think it is? 10. Yeah, because you see the word inflated, you see the word rate, you see the word per second, right? So all these movement words is telling us that is talking about something related to time. So dv over dt. And we know it's volume related because that cubic centimeters gives it away, right? So area is 2-dimensional, volume is 3-dimensional, everything else is 1-dimensional. Okay, positive or negative 10? Positive 10. Because why? Inflated, yeah, getting larger, right? Find the rate of change of the surface area of the balloon. What are we looking for? when the surface area is 64 pi? What variable is that? This S, yeah. Okay, so let's just go to the variable we're solving for, right? We're trying to solve for dsdt. So all we need for dsdt is radius and drdt. So if we have those values, we can plug in and we can find our answer. Do they give us the radius and the drdt? No. So we have to kind of do a little bit more detective work because it doesn't quite give us exactly what we need, but maybe there is some related information that can get to what we do need, right? We're trying to get to radius, get a drdt. So maybe the surface area and dvdt can help us arrive at those variables so that we can plug in and find dsdt. How do you think the surface area value can help us out? Can this, yeah, plug it into 4 pi r squared? What's the benefit of this equation? If I plug that 64 pi into here, I can solve for what variable? R, and that is the one piece of the puzzle that we need, right? So this is an indirect data that can help us get to what we really need, right? So we can do that and solve for R. So we'll do that in a second. But I want to kind of get a big picture here. How can this dvdt of 10, how do you think this can help us out? So if I plug 10 in for dvdt, and then I get the R that I'm going to get from here, I can solve for drdt. If I could get the drdt, then that's the last piece of the puzzle, right? Then I can get to my two values that I need to solve for dsdt. Okay, so let's do this first. I'm going to color code and show what our first step is. So we're going to take that 64 pi, insert it in for S, and see if we can solve for R. Everybody see what I'm doing here? Just replacing 64 pi in for S. And the reason that we're doing this is because we're trying to get to one of the variables that we need for our final equation. Okay, divide both sides by 4 pi. (16) equals r squared. Take the square root. R must be equal to what? 4, yeah. Technically plus or minus 4, but -4 doesn't make sense since we're talking about a radius that is a positive value, that's a physical length. Okay, so now we have that piece of the puzzle figured out. Now let's go to dvdt, right? Because we know that dvdt is holding the other piece of information that we need. So I'm going to take this, insert it into this equation, and see if I can figure out what my drdt that I need. I can now substitute R, right? I just found R. R is 4, so I can plug that value in. Okay, multiply this out. I get 4 times 16. That's going to be 64. All right, keep going. We want to solve for drdt, so what can we do next? Okay, divide by 64 pi. Now, 10 divided by 64 pi. Okay, here's something that I want to point out because I keep seeing this mistake. Where do you see the pi located? Denominator. Okay. And it needs to be in the denominator because we're dividing that 64 pi over, right? It's 64 is in the denominator, pi is also in the denominator. So as you reduce and simplify, make sure that your pi stays in the denominator. The reason why I say that is because I think we're more comfortable. We feel like the pi needs to be in the numerator. So I see some students, they do this problem and they feel, wait, that pi looks out of place. So they start moving that pi up top, and that changes the entire value of the problem. So it doesn't mean that pi is always in the denominator, but if algebraically, if pi ends up in the denominator, make sure you know that it stays there, because algebraically that's where it belongs. So if I reduce this 10 over 64, I get 5 and 32, but the pi is still in the denominator. So I have dr dt being 5 over 32. So that's the results of the second piece that I need. So now everything I need is in front of me, right? I can now solve for ds dt because I have r, which I got from S. I have dr dt, which I got from my dv dt equation. So now final piece is just putting all that to equal my equation. Okay, 8 times 4 is 32. 32 and 32 will cancel out, numerator denominator. The pi's also cancels out. I have a pi up top, a pi below. And now I'm left with ds dt is equal to 5 8 times 4 is 32. So, okay, what do you think our units of measure is going to be? Surface area. Focus on the word area there. So area is what? How many dimensions is area? 2, right? So centimeters squared. And then that's the surface area. Time is what? Seconds, right? Okay, so your homework, if you look on your calendar here, your homework says page 286, 291, 910, all the way to 38. I have all the homework filled out for you, so you can just do it directly in your packet. So this is on page 10. So I just copy and pasted it from the textbook, so you can just work directly on here. I'll send you a link to the new unit. There's a key. I have all the problems worked out on the key. Okay. All right. And tomorrow we'll continue working on more related race problems. All right, come get your phones.
So I have been looking, I just want to replay like when product rule and chain rule are together. Could you write me a column just so I can't picture how I look through the notes. Just so I can review for the.
Wait, what do you mean?
Like, okay, so I look on the review, there's a quotient and chain. I'm just looking for like a product one.
Okay, I got it. Got it.
That makes sense.
Right. So let's see. Let's see.
Then
Mhm.
this would be like the three square root would be the cube root would be the chain part, and then that would be, and then this would be the product.
Right.
And they would be multiplied together. So we have to do that first and then apply chain rule at the end.
Okay, exactly. Yeah. So you do product rule F prime G plus F G prime, and then within product rule, the F prime will be where the chain rule is activated.
Perfect.
Yeah.
Thank you.
Mhm.
You have this part, I can plug this.
I do, yeah. If you leave it here, I can have it on.
Okay, thank you. Yeah, I'll just grab it.
Okay.
Yeah. Not Worcester. I know.